Okay, so now what we're going to talk about is determining something called empirical formulas. Empirical generally means it comes from experiment. That's what it kind of means. Empirical data, you'll hear people throw that around. That means data that comes from an experiment or an observation. But what we're dealing with is an empirical formula is the smallest whole number ratio of elements in a compound. For example, water has a ratio of 2 to 1, hydrogen to oxygen. That is the smallest ratio, but hydrogen peroxide actually has a ratio of 2 to 2. So the smallest, the empirical formula of hydrogen peroxide, it's really HO, where it's 1 to 1 ratio. Okay, H2O2 is what's referred to as a molecular formula, and we'll get to that later. So what is the empirical formula of C6H12O6? Well, that's not the smallest ratio, 6 to 12 to 6. The smallest ratio would be divide all of that by 6, where it's 1 to 2 to 1. So the empirical formula would be CH2O. Remember, ones are understood. So that's an empirical formula. It is the smallest whole number ratio of elements in a compound. However, it's not all going to be as simple as that one. That's a simple one. If I give you the mass of each element within a compound, what you're going to do is you're going to either find the mass. If I give you a percentage, you're going to assume it's 100 grams, so that means percents turn into grams. Remember, mass cannot be created or destroyed. You're going to convert the grams to the moles, which we've been practicing. We've been doing mole conversions. And then here's the big key. You're going to divide the number of moles of each element present by the smallest number of moles of any of the one elements. Any element, whichever element is the smallest one, divide by that one. Okay, and that'll make most sense for doing this. And if you don't get a whole number integers, what you're going to do is you're going to multiply those ratios by a whole number to create integers. Because you have to have whole numbers. You can't have H1.5, O 2.9. It has to be whole numbers. And so we're going to come up with a way to figure that out. So, from experimental data, you're going to use the grams of each element. You're going to change it from grams to moles. Then you're going to set up a ratio where you divide by the smallest moles, and that will give you the empirical formula. So it's kind of a combination of what we've been doing with molar mass and mole conversions. So, compound contains 4.5 grams of carbon and 1.5 grams of hydrogen. What is the empirical formula? So, 4.5 grams of carbon. We're going to change from carbon grams into moles. Molar mass of carbon is 12. We're going to divide that out. Now here's the thing about hydrogen. Here, this hydrogen is part of a chemical compound. It is just H. It is not a Brinkelhoff element when it is an empirical formula. There are no Brinkelhoffs in empirical formulas. Never. So it weighs 1 gram for 1 mole. So I have 1.5 moles of hydrogen. I do 4.5 divided by 12, and I get 0.375 moles of carbon. So I found the moles of everything. Then I'm going to set up a ratio where I take 1.5 moles of hydrogen and I divide by 0.375 moles of carbon, and that tells me my ratio. 1.5 divided by 0.375 is 4 to 1. Now notice I wrote it as a proportion, or I wrote it as a ratio. That's 4 hydrogens for every 1 carbon. Because carbon on the bottom, hydrogens on top. I have more hydrogens, so I have 4 times as many. The empirical formula, the way you write it, is you turn those into subscripts. C1H4 or H4C1, and you can drop the 1s. Doesn't matter the order you write them in, as long as the 4 is by the H and the 1, which is understood, is by the carbon. Okay. If they give you a percent, what you're going to do is assume that you have 100 grams, and that gives you the grams, and then you just keep going exactly like we've been doing before. Okay. So 40% carbon, I'm going to assume 100 grams of a compound. That means I have 40 grams of carbon, 53.3 grams of oxygen, and 6.7 grams of hydrogen. And I'm going to, again, change everything into moles, recognizing that hydrogen is 1. Oxygen is also not a Brinkelhoff here. and carbon, never a Brinkel off. I got 3.33 moles of carbon. .33 moles of oxygen, and then I have 6.7 moles of hydrogen. Now these two are, I think it's pretty obvious if I divide that out, that's a 1-to-1 carbon to oxygen ratio. If I take my 6.7 moles of hydrogen and I divide by the smallest number, which is 3.33, it doesn't matter which one I even choose. I can choose carbon or I can choose hydrogen or oxygen because they're the same ratio. Divide this out, I get a 2-to-1 hydrogen to carbon. So what I'm going to do is I'm going to use this number and this number and this number as my subscripts. H2O1, and the C has a subscript of a 1. You don't add them together. It's a 1 here and it's a 1 here, so it's a 1 here. So that's my empirical formula, or CH2O or COH2. Doesn't matter the order you write them in, whatever you like. Okay, so take a minute, see if you guys can do this one. Again, you're going to assume 100 grams. It gives you 43.7 grams of phosphorus, 56.3 grams of oxygen. Again, not a diatomic, not a Brinkel-Hoff. Phosphorus is 31. I get 1.41 moles. You definitely want to keep sig figs here. You definitely don't want to call this like 1.4. Okay, the more sig figs you have, the more it's going to be, the more easy it's going to be to understand. The easier it's going to be to understand how the ratios work out. So I would keep at least 3. Okay, so I've got my moles. I'm going to take the 3.52 moles of oxygen. I'm going to divide by 1.41 moles of phosphorus. And I get 2.5 to 1. So when you get a situation like this, the ratio is 2.5. I don't want you to round it up. I don't want you to round it down. I want you to call it 2.5. And the way I want you to write it is P1, because it has a 1, O 2.5. And then recognizing that I can't have a decimal, but if I take everything in here and I double it, I get P2O5. I have whole numbers then, and the ratio is still 2.5 to 1. It's just 5 to 2. So this is a way where you won't forget to double that one and double this one so that you get a ratio of 2 to 5. So you could, this is what I was saying, when you don't get a whole number integer as the ratio, I would write it out and then multiply by something to make it a whole number integer. So this is your answer. This is not an answer. It has to be a ratio of 2.5 to 1, but it also has to be whole numbers. Okay, so go ahead and see if you guys can do this one. 10.37 grams of boron, 23 grams of oxygen. Again, oxygen's not a diatomic here. It's not a Brinkel-Hoff. Boron, I don't know how much boron weighs, 10.8. I got 0.96. Again, I would not round that. I would call it 0.96. Because otherwise you're going to end up with weird ratios, and I'm going to call this 1.44. So take the bigger number, divide by the smaller number, and you get a ratio of 1.5 to 1. Oxygen to boron, so B1O 1.5, double it, B2O 3. Still a ratio of 1.5 to 1, but it's got whole numbers now. So a quick review. Empirical formulas are the smallest whole number ratio. To determine the empirical formula, assume 100 grams of a compound if they give you percents. If they don't, you'll get mass in grams. There are no diatomics, no Brinkel-Hoffs. Change the grams to moles. And then set up a ratio, and again, divide by the smallest number, and watch for whole numbers.